So think back to when you were in 7th or 8th grade and first learning how to do algebra. And suppose I gave you an equation like this, 2x equals 14. What would you do to solve it? Well, of course, you would divide by 2, and then you'd get the answer, x equals 7. And more generally, if you have an equation like ax equals b, you would solve it by dividing by a. And you'd get that x is equal to b over a. But there are a couple of special remarks that are worth making. One is that you have to treat the case where a is equal to 0 separately. If a is equal to 0, then there are actually two different possibilities. If b is not equal to 0, then you'd have an equation where 0 is equal to something that's not 0, and there's no x in the equation, so there's no x that's going to make it true. And so there's no solution in that case. But if b is 0, then the equation says 0 equals 0, which is always true, no matter what x is. And so there are infinitely many solutions. And so there are three different possibilities that we've considered now. There's the case where a is not 0, in which case there's one solution. There's the case where a is 0, but b is not equal to 0, in which case there's no solution. And then there's the case where a is equal to 0 and b is equal to 0, in which case there are infinitely many solutions. If this feels a little bit like linear algebra, it's because it is. This is the special case where there's just one equation and one variable. But it's interesting that even in this special case, you see the range of possibilities that you see in the general case. And then the second point that's worth making is that dividing by a is actually the same thing as multiplying by a to the minus 1, which is 1 over a. So the point here is that even though we think of division as being one of the four fundamental operations that you can do with numbers, it's something that you could possibly ignore. And any time that you want to do division, you could potentially rephrase it in terms of multiplication. All right, so let's get back to linear algebra. And suppose we have a matrix equation, ax equals b. This is the kind of equation that we've been studying. And so you might ask, can I just do the same thing? Can I divide by a and solve for x? And the answer is yes. Well, sometimes. Just like we saw in the simple case where there was this issue where a equals 0 and you couldn't divide by a, there's a potential similar issue for matrices, but it's a little more complicated. It's not just when a equals 0. There are other cases where you can't divide by a. And so for us, there are two questions we have to answer. One, when is it possible? And two, when it is possible, how do you do it? And there actually is a third question we could ask, which is, if it's not possible, what is the next best thing? It's going to turn out that there's an interesting answer to that question, which sheds a lot of light on the stuff that we've been doing up until now. So how do we make this work? Well, the first thing we need to do is introduce these special matrices called identity matrices. These matrices are always square matrices, so the same number of rows as columns, and they have ones down the diagonal with zeros everywhere else. So there's one identity matrix for each dimension. There'll be a lot of cases where you can tell what the dimension is just from the context, and in that case, you can just refer to the identity matrix as I. And what's special about the identity matrices is that they satisfy this property that when you multiply an identity matrix times a vector, you just get that same vector back. You should convince yourself that this actually happens, like do the calculation out. So for example, there are different ways of doing matrix multiplication, so you can pick your favorite way of doing it, and calculate the 2 by 2 identity matrix times x1, x2, and what you should get is just x1, x2 again. And a similar thing works for matrix multiplication. If you have a matrix A, then you can multiply by an identity matrix, and you'll get A again. And remember that you can multiply matrices in different orders, and you might potentially get different things. And so we also can say that A times I is equal to A. But there's a subtlety here, because when you multiply on the left versus multiplying on the right, the dimensions might be different. So for example, if A is a 2 by 3 matrix, then when you multiply it on the left by an identity matrix, it needs to be a 2 by 2 identity matrix. Whereas if you multiply it on the right by an identity matrix, it would need to be a 3 by 3 identity matrix. So it's useful to think of the identity matrices as playing the role of the number 1 for matrices. Like when you multiply by 1, you get the same number back. And in fact, there is a 1 by 1 identity matrix, which is just the number 1. But it's important to remember that for matrices, there isn't just one identity matrix, there's a different identity matrix for every dimension. So remember that with ordinary numbers, dividing by a number is the same thing as multiplying by the reciprocal. So if we want to do something similar for matrices, then we need to come up with a concept of a reciprocal of a matrix. Except the commonly used term for it is inverse. So how do you talk about reciprocals without talking about division? Well, one way to do it is that you can say that the reciprocal of a number satisfies this special property that when you multiply a number times its reciprocal, you get 1. So for matrices, we can take a condition like this to be the definition. So we say that an inverse of a matrix A is another matrix A inverse, which when you multiply A times A inverse, you get an identity matrix. And again, because multiplication can be done in either order and you potentially could get different things, we have to make sure that you get an identity matrix no matter which way you multiply. So this seems like a reasonable definition, but there are some questions that pop up immediately. So one question is, do they exist? Can we even find a matrix like that? And then a second question is, if they do exist, are they unique? You'll notice that I said an inverse instead of the inverse because we don't yet know for sure that it's unique. So we'll get to these questions in a second, but first I want to show you how useful a matrix inverse can be if you have one. So the idea is that if A has an inverse, then you can solve a matrix equation AX equals B just by multiplying both sides by the inverse. And then, because A inverse times A is equal to the identity matrix, and I times X is just X, this gets us X by itself. X is just equal to A inverse times B. Now note that in this calculation, I used the equation A inverse times A is equal to I. The other equation, A times A inverse is equal to I, comes up when you verify that this actually is a solution. In other words, I'm going to take this formula for X and substitute it into the equation AX equals B and check that it works. And when I substitute it in, I get A times A inverse times B is equal to B, and I can use the fact that A times A inverse is equal to the identity matrix, and the identity matrix times B is B, so it works. So this is pretty good. This means that if A has an inverse, it gives you a simple way to solve equations AX equals B. You just multiply both sides by A inverse. But there's a couple of points that are worth noting. One thing is that the fact that we're able to find a solution means that a solution exists. So you know how we talked about how systems of equations sometimes don't have solutions? Well, that can't happen when A has an inverse. And then the other thing is that this formula, X equals A inverse times B, that's going to be a specific vector. You're given the A and you're given the B. So A inverse times B is a specific vector. There are no free variables in there. So not only is there a solution, the solution is unique. And this is the case for all B. So another way of saying that is that if A is invertible, which means that it has an inverse, it gives us a correspondence between X and B. For every B, there exists exactly one X, such that AX is equal to B. It's helpful to think about this in terms of transformations. If you have a vector B on the right, then you can multiply by A inverse to get the corresponding vector X on the left. And then that vector X is characterized by the property that when you multiply it by A, you get B back. So the linear transformations that correspond to A and A inverse are inverse transformations in the sense that they cancel each other out. And this isn't just a nice picture, it actually gives us a good way to think about how to calculate A inverse. So let me explain that. Remember that the columns of a matrix can be found by multiplying that matrix times the standard vectors, the E1, E2, E3, and so on. And so to calculate A inverse, we would calculate A inverse times E1, A inverse times E2, and so on. So in terms of this correspondence, if we put E1 on the right, then the corresponding vector X on the left is A inverse times E1. So in other words, A inverse times E1 is the solution to the equation AX is equal to E1. And that solution better be unique, or otherwise A doesn't have an inverse. And of course, the same thing goes for E2, E3, etc. But now this is pretty great. What this tells us is that if we want to find the first column of A inverse, we have a system of equations we can solve to find it. And we know how to solve systems of equations. We do Gauss-Jordan elimination. So this is pretty great. You solve this system, you get the first column of A. Then you do it for E2 and you get the second column of A, and so on and so forth. This might sound a little bit tedious, but later I'll show you how you can solve all of these systems at the same time. Okay, so let's look at an example. And just so you know, I am going to show you a faster way to do it a little bit later. But right now, I just want you to see what happens when you directly implement the process that we just discovered. So to get the first column of A inverse, we want to solve the equation AX equals E1. So when you plug in the numbers for A and E1, this is what you get. And so you would solve this by doing Gaussian elimination on an augmented matrix. And when you do that, this is what you get. Remember that it's totally fine to use Wolfram alpha for these calculations. But the result that we get, 3 minus 2, that's the first column of A inverse. And for the second column, we just do the same thing for E2. So that means you write down the augmented matrix with E2 on the right, you do Gauss-Jordan elimination, and the result is the second column of A inverse. So now we have the columns of A inverse, we can write down what A inverse is. And there it is, and remember that you can always double check that it works by multiplying A times A inverse. So now suppose there was a part B of this problem that asks you to solve AX is equal to 2, 3. Now that we already have A inverse, we can solve this just by multiplying both sides by A inverse. And so then the solution is that X is equal to A inverse times 2, 3, and you can calculate A inverse times 2, 3, and we get the solution. And yet again, this is something where you can check your answer by taking the matrix A and multiplying it times this vector, minus 6, 5, and you should get 2, 3, and that tells you that it actually is a solution. All right, so I promised you I would show you a quicker way to do it, and so here's one. You can basically do all of the steps of solving for E1, E2, E3, and so on at the same time by putting the entire identity matrix on the right. So think about this. The columns of the identity matrix are E1, E2, E3, and so on. So if you put the identity matrix on the right, then you really can think of that as solving for all of the columns at the same time. And then when you get it into reduced echelon form, if A is invertible, the system will look like this. You'll now have the identity matrix on the left and A inverse on the right. There's really nothing magic here. It's really just doing the same process as before, but combining the different steps into one step. So in the example that I showed you, you would have this as your starting point. And when you do the Gauss-Jordan elimination, you would get this as your reduced echelon form, where you have the identity matrix on the left and A inverse on the right. But there is something that we learn by thinking of it this way. And that's that the only way this can happen is if A is a square matrix. There's no way that A can turn into the identity matrix when you do Gauss-Jordan elimination unless A is a square matrix, because the identity matrices are square matrices. So A has to be a square matrix to be invertible. So if you have a matrix that's not a square matrix, then you don't even have to worry about this. It's definitely not invertible. But then on the other hand, being a square matrix is not enough to know that the matrix is invertible. The actual condition that needs to be true in order for this process to work is that the reduced echelon form of A needs to actually be the identity matrix, which occurs exactly when there's a pivot in every row and in every column. And then there's something else that you're going to want to know, which is that there is a special formula for 2 by 2 matrices. If you have a 2 by 2 matrix where the entries are A, B, C, D, then the inverse of A is 1 over AD minus BC times this matrix, where the way that I think about this is that you've swapped the D and the A, and you've minused the B and the C. And you can just sort of remember that that's how it works. You swap the things on the main diagonal, and you minus the things that are off of that main diagonal. And then you have to divide everything by AD minus BC. There actually isn't a great explanation for where this formula comes from, other than just a brute force calculation. If you sort of go through this process of doing Gauss-Jordan elimination on a general matrix with A, B, C, D as the entries, then this is the formula that you get. But one interesting thing that comes out of this is that you've got this expression AD minus BC in the denominator. That's obviously going to cause problems if AD minus BC is equal to 0, but that turns out to be exactly the condition that tells you whether or not A is invertible. So A is invertible if AD minus BC is not 0, in which case this is the formula for the inverse, and A is not invertible if AD minus BC is equal to 0. This expression AD minus BC is something that we're going to come back to later in the course. It has analogs in higher dimensions, and it plays an important role in the subject. But we won't get into that now. For now, the important thing is that when you have a 2 by 2 matrix, you have this special formula, which is going to be the quickest way to find the inverse. And if it's a 3 by 3 matrix or larger, then the quickest way to find the inverse is going to be to do Gauss-Jordan elimination. All right, so there's one more quick thing I wanted to mention before ending. And that's that I wanted to say something about how the process of taking inverses interacts with matrix multiplication. So suppose that you have two matrices, A and B, that are both invertible with the same dimension. So then you could multiply A times B, and you could ask, is AB invertible? And the answer is yes, it's invertible too, and there is a formula for it in terms of the inverses of A and B. And this is the formula, that the inverse of AB is B inverse times A inverse. So it's important to notice that the order got reversed. That might seem a little counterintuitive, so it's worth going through the process of checking why this happens. From the algebraic point of view, when you multiply B inverse A inverse times AB, you see that you can cancel A and A inverse, and then you can cancel B and B inverse. And so you do just get the identity matrix. And a similar thing happens when you multiply the other way around. But it's also helpful to think in terms of transformations. When you multiply a vector times AB, that means you multiply by B and then multiply by A. So how do you reverse that process? Well, because A was the thing that you multiplied by last, you would first reverse that, and then you would reverse multiplication by B. It's basically the same principle as to, like, if you put your socks on first and then put your shoes on, how do you reverse that? Well, you would take your shoes off first and then take your socks off. Think about it. All right.